Hello everyone, welcome to my channel. So in our previous electromagnetism part 1, we have seen about what is by electromagnetism. So what is Oersted experiment? So this is the Oersted experiment. So the properties of the magnets, the magnetic lines, the magnetic field, which is having a dipole. And next we have seen about the magnetic flux, which is the magnetic lines, number of magnetic lines passing through an area, and which is denoted with the units as Weber. And next we have seen the magnetic flux density, that is the formula magnetic flux density B is equals to magnetic flux phi by area A. So from this we have written the SI units as Weber per meter square. So this Weber per meter square can be written as Tesla. Next, now as yesterday what we were discussing is, if this area is having a certain angle, if this area is having a certain angle with an angle of theta, then the formula will be phi is equals to BA cos theta. That means there will be a variation of magnetic flux passing through that area. Now if you see in this first picture here, as there are number of lines passing is 1 2 3 magnetic lines are passing, but now when it has been converted to a certain angle with an angle theta with respect to its normal, so this is the surface, normal surface, and this is the perpendicular to that normal. Now it is making an angle theta. Now if you see here, only two lines are been passing out. Now what happens if it is like this? Now what happens if it is like this? Now here the angle between the normal of this area, that is the perpendicular line of this area, to this magnetic line is exactly 90 degrees. Now can you see any lines passing through it? Yes. So there is no lines passing through that area, so it will be 0. As there is no lines passing through it, the magnetic flux will be 0. Now how can we prove that? See, as the angle is 90 degrees, so as the angle is 90 degrees, so the theta 90. Now substitute in this. Now what we'll get as theta is equals to 90 degrees. We have a formula that is phi is equals to BA cos theta. So phi is equals to BA cos 90 degrees. According to the trigonometric values, we have that cos 90 is 0 into 0. So phi is equals to 0. See, as there is no lines passing through it, so the magnetic flux, as there is no magnetic lines passing through it, the flux is 0. Now if the angle is 0 degrees, 0 degrees is this one. So this is the normal, and the magnetic flux and the normal of this area are in a same line. If it is the same line, then the angle will be 0 or 180 degrees. So we take it as 0. Now substitute, if theta is equals to 0 degrees, then phi is equals to BA cos 0 degrees. So phi is equals to BA cos 0 value is 1. So phi is equals to BA. That is, if the angle is 0 at 0 degrees, the flux will be maximum. Remember, this may ask in your competitive examinations. And if the angle is 90 degrees, then the flux will be minimum. Okay, so these are the two important points that you need to know. But if it is with a certain angle like 45 degrees, 60 degrees, or any 70 degrees, then there will be a variation of value. By taking the trigonometric ratios, that is the values, you will find out the magnetic flux. Next, so this is what we have seen in a previous part 1 video. Now coming to the next part is the magnetic lines, to find out the magnetic lines around a straight wire. Now current carrying wire produces magnetic field. Now we have three types of situations over here, which is one is the magnetic field, that is which is passing through a straight line, and another one is a circular loop. I will show you what is the circular loop, how it will be, and another one is a helical structure shape, a helical structure shape which we call it as solenoid. Now let us see one by one how does the magnetic field be in a straight line, a circular loop, and in a solenoid. So before going to that, you need to know about the right hand thumb rule. Right hand thumb rule. So what does the right hand thumb rule? So this is the right hand thumb rule. This is my right hand. So thumb rule. This is said to be called as a right hand thumb rule, just like a thumbs up. So right hand thumb rule. Now, in case of a straight line, I am talking about a straight line. In case of a straight line, if the current is traveling in a straight line, that is in this way, as it is traveling straight, the current represents the thumb, and the curved fingers, these curved fingers represents the direction of magnetic field. Yes, the direction of magnetic field. So the thumb which represents the current. So whenever there is a straight line, you have to make sure that the thumb should be upward. That is, if the current is going in upward direction, so make your thumb upward. If it is moving in downward direction, make your thumb downward. Okay. Next, what will be the direction of this straight line? That is the curved fingers. If you represent the curved fingers, these curved fingers will be the direction of the magnetic field. Now one example going to show you here. So this is a straight wire. Assume it is a straight wire and the current is moving upward direction. Now what will be the direction of the magnetic field that we need to represent in a diagrammatic form? Now this is the upward direction. So current. Thumb represents the direction of current and it is moving in upward direction. And this curved fingers is moving like this. So how can we represent in this diagram is in this way. We can represent in this way. Now if it is moving in downward direction, now here the same what we have to do, where you have to represent the thumb, up or down? Yes, you have to represent your thumb down. So as you represent your thumb down, it represents in a opposite direction to this. So in the same way, if you make it in a okay, now here as the current is moving in upward direction, if you see a straight wire, so I am representing it in upward direction, that is it is moving in upward like this. So the current is traveling in upward, that is towards your direction. As a video which you are seeing, it is moving in towards your direction. So when the current is moving in out of the page, when we represent the out of the page, we represent it as a dot. So this is the symbol for which the current is moving in upward direction, that is which is in upward. And if the current is moving in downward direction, that is moving down, which is moving down, so it is represented as into. Don't forget that dot is which is in upward and into which is the down of the page. Simple how can you remember clearly is into means into the page and dot out of the page. So into is into the page and here dot is out of page. Now let us see the first case, as we have a dot which is coming in outward. So what will be the direction of the magnetic field? So as we know that the magnetic field will be represented in a circular loops. Now what will be the direction of this? Simple. What we have to do is we have to take the right hand thumb rule. So right hand thumb rule, as the thumb current is moving in upward direction, so we have to place it as like this. So upward direction, and see what is the direction, as it is moving in clockwise or anti-clockwise. So as the thumb is up, it is moving in anti-clockwise direction. So we have to represent it as like this. So anti-clockwise direction, anti-clock direction. Now what will be the direction of the magnetic field which is moving into the page? The current which is moving into the page, that is inside. Simple. Into the page, the thumb should be represented as down, and this is the direction of the magnetic field. As if you see my finger, the curved fingers, as it is moving in a clockwise direction. So as it is moving in a clockwise direction, so this is the direction of the magnetic field, which is clockwise direction. The same way for any direction, whether it is a sidewise or left or right, up or down, the direction of the magnetic field can be find out with the help of the right hand thumb rule. For example, think that the current is moving towards the right side, like this. So the current is moving towards the right side. Now you can see it clearly. As the current is moving towards the right side, now we have to find out the magnetic field. How can you find out the magnetic field? Simple. By using the right hand thumb rule. So the thumb represents the direction of current, and the curved fingers represent the direction of magnetic field. So place your thumb here, and the curved fingers represent the direction of magnetic field. As if you see on two sides, side A, side B, the magnetic field will be coming out to the A and entering into the B. As it is coming out and it is entering into the B, so the magnetic field will be moving in this direction, coming from down and going up. The thumb represents the direction of current. For example, if it is in opposite direction, simple. Represent the thumb in this direction, and the curved fingers will moving up and going down. Okay, so this is the magnetic field direction, how to find it for a straight line. Now coming next to the circular loop. So how can we find it for the circular loop? Coming in for the circular loop. Circular loop and solenoid both represents the same. Here the right hand thumb rule will be taken, but here the right hand thumb rule will be opposite. What will be opposite here is, we have a thumb and we have a curved finger. Previous what we have done, as the current is moving straight, we have to take it as a thumb. But now when it is moving in a circular round, the current is moving in a round and round and round. Now what we have to take, should we take a thumb or should we take a curved fingers? As the current is moving round, yes. As the current is moving in a circular path, like in a curved path, we have to take the curved fingers. That is, in a circular loop or a solenoid, the curved fingers will be represented as direction of current, that is current direction. Now what will be the direction of the magnetic field? Yes, the thumb will represent the direction of magnetic field. This is the direction of the magnetic field. Now I have a small demonstration over here. So this is a wire. Now this wire is been rounded up like this in a circular form. Okay, now it is a circular loop. Now the two ends are being connected to the terminals of a battery or a source, positive, negative. So one is the positive and another one is the negative. Now what will be the direction of the magnetic field in the case of current carrying loop? Now the important thing you need to find is, let's take a bigger circular. Yes, now this is a circular loop. So this is a circular loop, as the current which is traveling into this loop will be taken as two directions. One is a clockwise direction and another one is anti-clockwise direction. Now for suppose if the current which we are passing through it is passing towards like this in a curved path from point A, taking it as point A and point B. So as it is passing from point A to the point B, as we represent the curved fingers starting from point A to the point B. This thumb will represent the direction of magnetic field which is passing inward. Now if you see here, as shown in your textbooks, this is the curve. Half of the circle half will be represented in a downward direction which is connected to the batteries, starting from here and ending to here. As the current is moving in this direction, the magnetic field will be towards like this. That means if it is passing from here to here, then the magnetic field will be inside, as it is passing like this. If the current is passing in opposite direction, from here to here, then the current is passing from here opposite to this, the magnetic field direction will be like this. So as the current is passing like this, the thumb represents the direction of magnetic field and it will be inside, that is which is coming out of the circle. So if it is going inside, it is in clockwise direction. If it is coming outside, it is represented as a anti-clockwise direction. Now here, as you can see, if we are taking in a paper, as the current is coming in outward direction, so as it is coming in outward direction, we have to represent a dot or a circle, dot or into. As if it is coming out, we should represent as a dot. And as the current is going into this page, it is coming out of this and going into this page, so we have to represent as into. Now draw the magnetic field lines for these two as were present just now, as we have shown in this one. Let's take one concentric circle. So out of the page, which is this one, which is in anti-clockwise direction, and this is into the page which is said to be called as clockwise direction. Now if you observe here in the middle, as a current is coming through this wire and ending into this, the resultant of these two magnetic fields gives the straight direction, which is shown like this. Now if it is in opposite direction like this, what I have shown you here, the current is coming out of the page which is represented as a dot, and the current is moving into the page which is said to be called as into. Now here, as the current is coming out of the page, we have to represent it as anti-clockwise direction, and the current which is going into the page, into this page, this is into, which is represented as clockwise direction. Now the resultant of these two directions will be in downward, like towards my side, which is represent this one. So in a circular loop, you don't get confused over here. So we have so many activities that will be shown in the next video. In the next video, you will be having so many of activities. And next, coming to the next solenoid. Solenoid is a copper wire which is represented in a helical structure. Helical structure in the sense is this copper wire is represented like this. Now this is said to be called as a solenoid. Now this is a solenoid which is in a concentric circles having like this. Now if a current is passed into this wire, now these two are be connected at the positive terminal and this is connected to the negative terminal. As the current passes into this solenoid, it produces a magnetic field. As in a circular loop, one circular loop, as a magnetic field is traveling in a straight line. So as there is many circular loops, all it represents in a straight line, and that solenoid gives the direction of the magnetic field, which is represented as a similar to the bar magnet. That is, how does a bar magnet produces a magnetic field? This I have shown you in the previous part 1. As it moves from the north and it ends to the south, how does it travels here? The same way also it creates a magnetic field lines around it, which is passing from one point to the another point. Which is passing from one point to another point. So in this case, as the current is traveling in this direction, so we have to take this side will become as a north pole and this side will become as a south pole. And as it is passing from here to here, that is the magnetic lines will pass from one end of the solenoid, that is one end of the solenoid, to the other end of the solenoid. It passes through it like this, north to south. And what about the magnetic lines which are having inside the loop? Inside, what happens to it which is passing inside the loop? Simple. If it is from outside, as it is passing from north to south, and inside, yes, it is passing from south to north. Now as if you see here the magnetic line, the same line which is passing from north to south, and inside it is passing from south to north. So hence what we can say is the magnetic lines are a closed loop. So how can we say it as a closed loop? As here in a solenoid experiment. So if anybody asks you, how can you prove that the magnetic lines are a closed loop with the help of a solenoid? So if you pass a current through a solenoid, it produces a magnetic field and just behaves like a bar magnet. So in a solenoid, the magnetic lines passes from one end of the solenoid and ends to the other end of the solenoid, just like as I have shown you with the figure. So it passes from one end to the another end. As the magnetic lines are starting, it is the north pole. As the magnetic lines are ending, it is the south pole. And inside the bar magnet, these lines are passing from south to north. As we can show this by having a magnetic compass or iron fillings or iron powder. With the help of these two experiments, we can show the lines of the magnetic which is outside and which is present inside. So by this experiment, we can prove that these magnetic lines are a closed loop. So till now what we have discussed here is, so we have discussed yesterday in part 1, we have discussed about Oersted experiment, the magnetic lines, the magnetic field properties, and the magnetic flux, and the magnetic flux densities. What about the angles? So if it is a maximum, the angle will be 0 degrees, and if it is minimum, the angle will be 90 degrees. And coming to the current carrying wires, which is in a straight circular solenoid, by the right hand thumb rule we have discussed that. So out of the page which is represented as dot, and into the page which is represented into the page, going down of the page. Next, which is anti-clockwise, clockwise. And next, coming to the circular loop and the solenoid, the same thumb rule we have represented, but little bit different over here. So remember one, the right hand thumb rule, see the direction of the current if it is moving in a straight line or curve. So if it is moving in a straight line, use the thumb as the current. If it is moving in curves, use the curve as the finger. These curve fingers as the direction of the current. Automatically, the another one will be represents the direction of the magnetic field. So next video we'll be having a small exercise about these, how to find out the magnetic field lines, how to find out the current, that we will see in the next class. Now right now, thank you for your time. Please subscribe the channel. More interesting videos will be near you. Thank you very much.